In this video, we'll discuss types of intermolecular forces, often abbreviated IMFs, and we'll specifically focus on London Dispersion Forces. So let's start out reminding ourselves about what IMFs are. They are the force of attraction between separate molecules. I like to use the word separate, reminding us that we need at least two molecules to have any intermolecular forces. If we don't have two molecules, all we can draw are covalent bonds, not intermolecular forces. So, types of IMFs. One kind of IMF is a dipole-dipole intermolecular force. This occurs when we have polar molecules, and one end of the polar molecule, the partially negative end, attracts to the partially positive end of another polar molecule. In this polar molecule, we could call this a dipole. Dipole, of course, means a pole with two opposite ends, a partially positive end and a partially negative end. This molecule would also have a partially positive and partially negative end. Negative and positive attract. When we have an attraction between separate molecules, that's an intermolecular force. Here we have an attraction between two dipoles, so this will be a dipole-dipole intermolecular force. Another kind of intermolecular force is actually a subset of dipole-dipole forces, and this is hydrogen bonding. The reason it gets its own name is because it's such a strong kind of dipole-dipole force. This occurs when the hydrogen on one molecule attracts to a fluorine, oxygen, or nitrogen on another molecule. Why is this such a strong kind of intermolecular force? Well, if you look at the periodic table, you'll notice that fluorine, oxygen, and nitrogen are the most electronegative elements, whereas hydrogen is the least electronegative nonmetal. So, bonds between hydrogen and fluorine, oxygen, and nitrogen will be especially polar bonds. The electrons are going to be really pulled towards fluorine, oxygen, or nitrogen. So therefore, the fluorine, oxygen, or nitrogen will have a strong partial negative charge, whereas the oxygen has a strong partial positive charge. And the most polar bonds are going to form the strongest IMFs. Now let's take a look at this with an example of a really common molecule that undergoes hydrogen bonding, water, or H2O. In an H2O molecule, of course, the oxygen is more electronegative than the hydrogens, so it pulls the electrons towards it, and it acquires a partial negative charge. If we were to diagram another H2O molecule right next to it, we would see that the partial positive on one hydrogen, one molecule, would be attracted to the partial negative on the oxygen of another molecule. And that right there is going to be the intermolecular force, and that's the hydrogen bond. Now, let's of course remember that's not the same thing as a covalent bond. And the covalent bond we will diagram with a straight line, whereas the hydrogen bond, or any intermolecular force, we diagram with a dotted line. Part of the reason we do that is to indicate that the intermolecular forces are not as strong as covalent bonds. Indeed, a hydrogen bond, the most strong kind of intermolecular force, is still only 5% the strength as a covalent bond. So just reminding ourselves, intermolecular force is not as strong as covalent bonds, even hydrogen bonding, which is the strongest. Now, the next kind of intermolecular force is the one we'll discuss for the rest of this video here, and that's a London Dispersion Force. So, in order to discuss London Dispersion Forces and how they come about, we're actually going to take a big step back and talk about atoms and what atoms look like. So, let's get rid of this, and let's pull this up here. So, what do atoms look like? Well, the challenge with answering that question is that atoms are so super tiny that any representation we make of atoms is not going to be perfect. Take a Lewis dot diagram, for example. This is a great way of showing the valence electrons in an atom, but of course it doesn't show all the electrons, it doesn't show where they're located, and it doesn't show the nucleus. We could draw a Bohr diagram. This is a great way of showing all the electrons in an atom, and particularly what energy level those electrons are in. But electrons are not really located in rings around the nucleus, so this also has its drawbacks. Another way we could diagram an atom, and perhaps one of the better ways, is to do what's called an electron cloud diagram. An electron cloud diagram, you show the nucleus in the middle, which of course is very small in volume compared to the rest of the atom, and the electrons around the outside. Now, electrons are actually zooming all around an atom. They're not stationary. They're always in motion. So in an electron cloud diagram, we would show the electrons in motion somewhere like this. And of course, they'd be zooming around. They would be in their different orbitals, but they'd all be moving around. In reality, we would never be able to pick out an actual electron. So there's some advantages to the electron cloud diagram. Of course, that doesn't show us how many electrons we do have in an atom. But if this is what an atom looks like, atoms, of course, make up molecules. And so we can ask ourselves, what does a molecule look like too? And let's do the molecule Cl2. So Cl2, we could ask ourselves, what does it look like? We could draw the Lewis dot diagram. And if we were to draw that, we'd see we have one bond in the Cl2 molecule, and this bond is between two chlorine atoms. And because they're the same atom, then this would be a nonpolar bond. Because the electrons are shared evenly between the two chlorines. Neither chlorine is pulling harder on the electrons than the other. And because there's only one bond in the Cl2 molecule, if we only have nonpolar bonds in a molecule, then the molecule itself has to be nonpolar. So this will be a nonpolar molecule. So again, we said that neither of these chlorine atoms is pulling harder on the electrons than any other. So we could show this also, in addition to a Lewis dot diagram, with an electron cloud diagram. So here we have the two nuclei and the electrons zooming all around, and of course some of the electrons are shared between the two chlorines. Now, although neither of the chlorine atoms is pulling harder, because the electrons are moving all around, at one time or another, perhaps the electrons move around and they're more close to the atom on the left. If that were to occur, this atom on the left would end up with a partial negative charge. Why? Because electrons are negative and they just happen to zoom over to the atom on the left. And the atom on the right would have the electrons away from it. It would have a partial positive charge. We could diagram a dipole on that. What could also occur is that the electrons could zoom more around the atom on the right. And if that were to occur, the atom on the right would end up with a partial negative charge. The atom on the left would be partially positive. The dipole would be exactly opposite. So what we've seen here is that even nonpolar molecules like Cl2 could acquire a dipole temporarily. And not because any of the atoms are pulling harder, just because the electrons at one point or another might zoom more over to one side of the molecule than the other. Okay, so thinking about that, let's now ask ourselves if a molecule like Cl2 could experience any intermolecular forces. So let's put up some Cl2 molecules here and figure this out. So I drew the Lewis dot diagram of our two Cl2 molecules, and right beneath it, I drew the electron cloud diagram. So as you'll notice, I did not draw these electron cloud diagrams with the electrons evenly split between the two atoms. I drew them with the electrons zooming more over to the atom on the right. So this would have a temporary dipole with the atom on the right having a partially negative charge. And same thing for this Cl2 molecule over here. There would be a partially negative charge with the atom on the right, partially positive charge with the atom on the left. Now, what do we see here? On one atom, on one molecule, there's a negative charge. On the other molecule over here, partially positive charge. What do negative and positive like to do when they get near each other? Attract. And that's exactly what would occur here. There would be an attraction. This attraction is between separate molecules. So therefore, it is an intermolecular force. And the attraction, intermolecular force between these two temporary dipoles is called a London Dispersion Force. Or LDF. So this is what an LDF is. It's a force of attraction between separate molecules that happens just because electrons happen to zoom over to one side of the molecule and away from the other side. Okay, So let's talk about London dispersion forces briefly then, and summarize them. All right, so London dispersion forces. Whoops, let's get that nicely. All right, now, all molecules have electrons. So therefore, all molecules experience London dispersion forces. What we showed earlier was Cl2, a nonpolar molecule, but all molecules could have the electrons zooming over to one side or the other. So all molecules experience London dispersion forces. However, London dispersion forces are the only intermolecular force experienced by nonpolar molecules. They don't have permanent dipoles, so they can't have dipole-dipole forces, and they can't have hydrogen bonding as well. Now, you may ask yourself, how strong are London dispersion forces? And can we have different strength London dispersion forces? We'll answer that question in the next video. But hopefully this has given you a good idea of what London dispersion forces are, how they come about, and what kinds of molecules experience London dispersion forces.